then also there was that whole Frank Starling mechanism, that is, the more that was coming in the heart was gonna pump out that much, right? So if you're exercising, you're getting more venous return. That's what this is right here. You're bringing more blood back in to the heart, right? It's gonna pump that much more out. This is gonna be equal. And then, you know, those are the venous return. That was done by your skeletal muscle pump moving around, also your respiratory pump. Everybody remembers how the respiratory pump works? Moving on, what I'm talking about, thoracic pump.
By breathing.
And by breathing, you're increasing, this will be useful for the respiratory system. Breathing, you're increasing your thoracic cavity. In that case, it's bringing air in, but while you're doing that, you're also putting pressure on your abdominal cavity. That's the fact when you're doing CPR on somebody, you're actually doing that, you're moving the chest wall in and out. That's what's actually moving the blood out. Right? So, and skeletal muscle pump is just moving, right? When you're standing there, that's why your blood starts pooling and everything, right? And all your interstitial fluid, that's why you start to get edema. On the other side, right, you increase the amount you're pushing out per stroke, and then you can also do more beats, right? Increase your heart rate. And that mainly is going to be increased by your sympathetic nervous system. Right? There's a couple of mechanisms there, but mostly it's working, in this case it could be working on here it was working on the actual contractile cells in the heart, the ones that actually contract by increasing calcium over here. It was working on those pacemaker cells, right? You're increasing the action potential rate. How would you do that? If you want to depolarize faster, if you want to get the cell more positive, what kind of channels might you want to open? Especially in the autorhythmic cells, either one really, if you want to do it faster, which ones would you do?
Calcium?
What? You could do one or two things, right? Open sodium, right? That would cause a faster depolarization. And how about the sympathetic, right? That would be decreasing the heart rate. That would slow down that whole, so you'd hyperpolarize the cell a little bit. We also noticed that the parasympathetic was the normal tonic innervation, right? It slows down your heart naturally. If you remove parasympathetic input, your heart would beat, your natural pace of those pacemakers would be a little faster. That's why the heart, when you take it out of your body, when you do that sort of thing, it'll just beat a little faster because you remove the parasympathetic input. Right? So that's that was most of the lecture. The rest of it was that whole beating sequence. Heart, blood in, blood out, and then today we're going to start looking at how the blood is pushed out, right, to the entire system, right, moving out from the left ventricle into the aorta, and then that force, right, that's the pump that's going to push blood into all your, coming from the oxygenated blood is coming on the left side here, being gone into the left ventricle, and then being pumped out to all the oxygen and nutrient-starved tissues of your body, right? And you need a little pressure, you need a lot of pressure to do that, right? And that the pressure, all that pressure is from that left ventricle squeezer right there. That's where it's all coming from, right? So overall, when we look at the system, right, we want to kind of keep everything in mind, the big picture. So you got say here's the pump right here. It'll be the left ventricle, and then it's going to be going to all the body parts. What's a body part? Head. Now your brain, right? It's got to go up there. What's another one? Your heart itself, right? This is one of the first places it goes. Your heart as a tissue, right? Needs a lot of blood. It's going on like the whole renal circulation, the kidneys. Right? It's going to be filtered. The blood's going to be filtered. It's going to what's the so-called splanchnic arteries, which means the all your guts, right? Your liver, all your guts and stuff like that are right there. What else? Skeletal muscle, all over your body, right? It's just a general thing. Obviously, this is all over the body, but this is where the blood's going. Skin, all over the skin. So, pump. This is the whole purpose of the whole thing, right? Getting this pump, getting all your blood. This is what all this tissue needs. If it doesn't have it, what happens? You die. especially here and here. This is the quickest place you die, basically, right? If your heart's not getting the right muscle, then nothing else receives it, right? Your brain is the second one, right? It will shut down pretty quick. So all that blood is gonna go in as, you know, oxygenated blood through the arterial system. And then it's going to cool back, veins, right? Move up. Where is it gonna enter? And the vena cava here, this was the aorta here. And the vena cava is the superior and inferior vena cava into the right atrium. Right? From the right atrium, we're not really talking about this today, but the right ventricle. Lungs through that pulmonary arteries, and then back into the left atrium, right? That's the whole circuitry right there, right? It's all starting here. The driving force for all that is going to be that left ventricle, right? So keep the big picture in mind as we move through there, right? But also, this right here, we're gonna put a lot of pressure into the system, right? So starting looking at the first pressure we looked at, it's good looking at these charts, look at the pressure changes. You can look at the atrium here in blue, and that's the first little bump. Right over here was that first little contraction, right? So when you contract over there, you're decreasing the volume of that space. Not the volume of blood, well, you will decrease the volume of your blood too, but basically you're decreasing the volume of that space. When you decrease volume in the space, right, you're gonna increase pressure. That squeeze it down from a higher pressure area to a lower pressure area, right? Over there, that squeezes the last bit of blood in, right? And at that point, your ventricles start contracting without removing blood, right? It contracts, right? The pressure is increasing, it's increasing, until it reaches this pressure over here by the aorta, right? As soon as it exceeds the pressure in the aorta, we can move forward, right? You see the pressure in the aorta right here? It was dropping over here until that point, dropping a little bit. When those two meet, that's when the pressure is gonna go from the ventricle into the aorta right there. That's what's gonna blast open the aortic valves, basically, right? And then together, right, the pressure is increasing because the aortic pressure is increasing right here because it's filling up blood, right? It's the pressure, the blood pressure itself is increasing the pressure right there. Okay? Then at a certain point, as the ventricle's finishing squeezing the blood right there, the pressure starts to decrease. And then that's when the pressure of the aorta is gonna exceed the pressure of the ventricles at this point, right? And at that point, the blood drops back down, which closes those aortic valves. Right? And here, this is a little bit, we'll talk about this when we talk about the aorta, this little bump right here, but then after that, the ventricle pressure drops way down because it's relaxing, right? It starts to relax, it starts to dilate, the volume is increasing, right? When you're increasing the volume, you're decreasing the pressure, right? And then you also see, if you look at the aorta at this point, or the whole point when it was squeezing right here, slow filling started at some point of the atrium. Right there, you can see that rise a little bit, right? And at this point, you know, when the pressure starts dropping over here, that's when the AV valves must open, drop, because the pressure in the atrium and the ventricles started to, the pressure in the atrium started to exceed the pressure in the ventricles, right? And that's where it all dropped down in there. All right, so you look at these charts and you can see the whole sequence of events, the pressure changes, and the chambers, the containers, either the aorta from the ventricle to the aorta, and the pressure changes and the direction of blood flow, basically, right? So again, that first pressure change, the biggest one right there, the ventricle, the left ventricle, you're squeezing. It goes from this space to this space, creating an enormous amount of pressure. And pressure, this formula right here, pressure is inversely related to the volume. And again, not the volume of the blood here, we're talking about the volume of the space, the container. That's the driving force that's going to create that initial pressure, right, by changing the volume, right? So that contraction, again, just looking over the big picture here, contraction is creating that high pressure, and it's going to move towards the lower pressure area of the aorta at that point. Not that it's necessarily low pressure, it's just lower, that's all that matters. That's what's forcing that. So high to low, we're getting a pattern here. High to low, just like diffusion, but it's not like diffusion because this is like hydrostolic pressure. There's an actual force, fluid movement, bulk movement. It's not just little particles moving around on their own and moving toward an area of lower pressure. This is hydraulic pressure moving through here. All right? And then, again, pressure differences. Once the ventricle has contracted, the blood has gone from it, right? That is making the pressure drop a little bit. And then the pressure in the aorta at this point has exceeded the pressure down there, which would make the blood flow back in here, right? The blood would start to go in the area of lower pressure ventricles, except that the AV valves are there to stop that. Not the AV, semi-lunar valves, right? The aortic valve. Right? Pressure going from high to low. That's the big picture here. Right? So we look at the big picture like this. Right? We got the left side heart going to the system. We'll kind of ignore the whole pulmonary circuit, but that would have the same idea, right? You're leaving the heart, and then you're moving all throughout all the tissues in your body, right? And you're always going to be, you got to know that all this stuff right over here is lower than this stuff over here, and this is lower than this over here. This is lower than this. This is a little lower than this at that point, right? We're just moving from high, and we're going to decrease the pressure. That's the way it's got to be. We got to decrease that pressure as you move along, because otherwise the blood wouldn't flow there. Right? Coming back up, it's kind of the same thing going up. It's a lot, the difference in the pressure is a lot less. It's very low pressure moving up here, and there's other mechanisms to move it up. But ultimately, the lowest pressure is going to be right here, because this is where it all returns right there, right? So we look at this big picture, and we start to understand this. Right? But when we talk about pressure, right, when the heart squeezes out here, what's happening when we talk about the blood pressure? We're talking about the force of the liquid, the blood, the plasma that's exerted on the walls right there, right? You're creating a lot of pressure, just like if you put it in a water balloon or something, right? It starts blowing up because of the pressure on it. In the case of the blood vessel walls, they have some elasticity that'll kind of take away a little bit of that immediate pressure, but it is still fairly it's a tough wall right there that's going to withstand it, and that's going to create force over the wall. This is what blood pressure typically is, right? The pressure on the vessel walls right there. This is going to cause a lot of tension, right? So that's what we mean by blood pressure, right? So the blood's leaving the heart, it's causing that driving pressure, and that pressure is going to be maintained, right, throughout the artery. Right? So when we say systolic pressure, when we look at that right there, that's generally what's the immediate cardiac output right there, right? The stroke volume over there. And we talk about the diastolic pressure right there. That'll be the kind of pressure that's transferred over into the arteries. Right, so there's a lot of pressure on the vessel walls, and if there's pressure here, right, on those walls, right, it wants to kind of escape that, right? It's not compressible, so it's going to move toward the next area, and that's generally what's happening. This pressure differences, right? It wants to move toward the area of lower pressure. So big picture here. All these fancy things here. Q. Right, over here, this is where it explains all these things, right? Q, they often term flow, right? The flow of blood moving, right? It's going to move from an area of high pressure to low pressure right there. So we say it's directly proportional. That's that little at symbol right there. Directly proportional. I'll write that. Just keep that up in case it shows up again, right? Directly, this means proportional. Directly proportional. Because it could also be inversely proportional, right? Over there to the change in pressure, right? Delta P. Difference on one end to the other, right there. That's what that means right there. This is the pressure gradient. And this is flow. Right? So the flow is going to move from an area of high pressure, low pressure, right? And that formula means that the higher the pressure on one end, right, the more the faster, the more flow is going to be right there. Right? The greater the flow is going to be, right? So in this case, change in pressure in vessel 2, going from 90 to 10 is what? 90 minus 10, anybody get calculators? Like 80 over here, right? This one's 40, right? So the pressure here, even though it's kind of same size and everything, right? It's greater, it's much greater, right? It's just about the difference. It's not an absolute pressure, right? Because on this side over here, you go from 90 to 10, right over here, that's 80. This one's going from 80 to 100. If you do the math, you have a calculator right there, you can figure out that they're both 80, right? Even though the pressure difference is the same, right? So we're just looking at pressure differences, not the absolute pressure in anything. That's how blood is gonna flow in that direction, okay? And it's, the harder it is, the greater the flow, the greater the difference, the greater the fluid flow, right? There's gonna be more in there. All right, so. Pressure leaving the aorta again is gonna be the highest right there, and as you move through a system, right there, it's gonna decrease, the pressure is gonna decrease, right? And that's almost gotta be, we don't have to understand exactly why it's moving, but you know, if it's going from here to here, that means there's pressure. If it's going here to here, there's gonna be a pressure difference, right? Going from here to here, so on, right? There's always gonna be that pressure difference between two places, right, for blood to move. If it's not, then blood doesn't move, right, if there's no pressure difference. That's that chart right there. As you move away from the aorta, right, you're gonna decrease the pressure, continuously decrease the pressure, right? So like, as an example, right, here's your heart. Remember the aorta right here, you got those left and right coronary arteries coming right out of it, right? That's the first, basically, place coming out of the first systemic pathway right here, right? This is the one, this is the heart, blood flow to the heart supply, right? And then you look over here, say the left coronary artery goes down the LAD, the left anterior descending right here, under very high pressure. And it's gonna perfuse the capillaries in this case. Right over here, it's gonna oxygenate the tissue, and then the tissue is gonna like let off the metabolic waste, the carbon dioxide, and come back through the great cardiac vein over here, right? And it's gonna go around, the great cardiac vein is gonna come around. Eventually, all the blood in there is gonna pool with this coronary sinus. Over there, it's gonna dump directly into the right atrium right there, right? So pressure, obviously, over here is the highest, right? And then it's gonna decrease almost to very low when you get to the veins right there, but the veins are gonna have a little bit more over here than over here, and then the right atrium is gonna have the absolute lowest, because blood is gonna flow right into it, right? For all your other body systems, anywhere you think it's gonna be the same thing, right? From your, going up to your head, right? You got your carotid arteries, going up to your head, they're gonna split off into smaller internal carotid arteries, right? And they're gonna turn off into your middle cerebral arteries, right? They're gonna branch off, and then branch off into capillaries, come back down through similarly named veins until they go into the jugular, right? Into the brachiocephalic veins, everybody remember all that stuff, and then dump into your superior vena cava back in the heart, right? This will be the pattern right here. Okay, be a very high blood pressure in the start of any circuit that we're thinking. And then by the time it comes out of the capillary bed is veins, very low pressure, and the lowest pressure to get back to the heart has to be lower, right? So that's the whole sequence anywhere you look, right? The why question is that you're asking yourself, but why? Why? Why is it decreasing? Why is that pressure decreasing, right? You're moving through that whole picture right there. You know, it's kind of complicated, but ultimately the distance from the heart, right? You're starting off the left coronary artery, relatively big vessel, and you're gonna end up at the coronary sinus, right? So as it's going through there, right, it's gonna move through, it's gonna get small, vessels are gonna branch off a little bit until they're smaller things, until it goes into the capillary bed right here, and then it's gonna kind of pool up and get bigger and bigger, right? Something like this. This is the blood flow in here, right? And as we go, we can start to see pressure change. There's gonna always be enough to get into the capillary bed, right? And over here, it's just kind of pooling at the same pressure, moving back up, basically, because it's gonna be squished back up. But in this case, right, that's how you wanna look at it. You could look at it as one length, and pressure basically is gonna decrease, right? Because there's resistance. As the blood is moving through, there's friction moving against the vessel wall. And that's basically what's happening as it moves through the tubes right there. The blood, as it flows right? Even as nice, as smooth as the blood vessel lining is, right? There's some resistance against the vessel wall, as well as the, between the blood cells themselves, right? So the actual resistance, right, is gonna be, the contributing things to resistance, right, are the length, right? The length of the vessel is gonna matter. But for us purposes, when we talk about the whole system, it doesn't really matter about length. Your length is not gonna change in any kind of meaningful way. Like unless you gain like a lot of weight or something, you get more blood vessels, maybe your overall blood pressure, you'll have more resistance in all your arteries and stuff. But otherwise, on a day-to-day basis, the length is your entire blood vessel system. So that really doesn't matter for us. So we don't care. And then the second one is the viscosity of the blood. That might have like some kind of bearing if you were start taking EPO, right? Anybody know what EPO is? No, never heard of it? That guy, Lance Armstrong, he won all those races, mostly he was doping, he was like taking a drug. It's also a natural hormone that increases your blood cells. So you increase your blood cells, that's gonna increase your viscosity of the blood, right? So viscosity of the blood could be an effect, right? You could also just inject your own blood again, that's what they do now after I think they can detect that now too, but they could just they want to increase their levels of oxygen basically. So you can do that, or if you have anemia, you have less red blood cells, your pressure would be lower, right? The resistance around the blood vessels would be less right there. But the biggest thing is the diameter. Right? When you look at what the diameter is, if you look at the formula, I'm not going to give you the Postwell or whatever formula guy, but there's a big complicated formula that looks at the factors of resistance. The biggest thing is the radius of the tube, because that's like a power 4, right? So you increase it just a tiny bit, it has a huge effect. Right? The resistance is inversely proportional to the radius of the vessel. The bigger you increase this number right here, because it's on the denominator, you're going to increase the resistance. Right? Which means if you increase the diameter, you're going to increase or decrease? Increase the diameter. Are you going to increase the resistance or decrease?
Decrease.
Yeah, you're going to decrease it. Basically, the big thing. Basically, there's a picture right here, right? There's the water coming out. The pressure over here is going to be the same. It's gravity right here, but the volume is much bigger. You're going to have much bigger, better flow with that bigger diameter right there. Right? And that's what we're also going to change on a moment-to-moment basis. We just change, basically. So the flow, we're just going to be able to change the resistance by changing the diameter of the tubes for blood vessels, mostly the arterioles, as we'll see, right? So the flow, when we talk about the flow, it's directly proportional to the difference in pressure gradient, right? From high to low, and then it's inversely proportional to the resistance, right? Which is going to mostly for our discussion, we're going to talk about the resistance is going to be met by the diameter, right? Talking about blood flow, these are the factors of blood moving through this whole system right here. All right? Does that make sense so far? And the other thing about flow through the systems right here, there's the flow, that is the amount of blood passing through any area, right, within a given cross section right here, the flow rate over here. So if you had a big highway, right, you counted the cars for like 5, so you got a 5-lane highway, you said, well, if the cars are going by at a rate of 10 cars a minute, right? And if you had a 1-lane highway and you said they're going by at 10 miles a minute, right, you'd still have the same rate, right? But the flow might be a little bit, the speed that they had to match that, to make that, is going to be faster right here, right? So basically, when you're looking at the rate, that's a velocity thing, right? So miles per hour is speed, right? Velocity is centimeters per minute. Right? So speed is different from the volume passing through at any given moment. That's flow versus speed, right? That's going to depend, again, on the cross-sectional area. The flow is going to, the velocity is depending on the flow rate and the cross-sectional area. Miles per hour, centimeters per second, right? Or volume per liter, right, the volume of blood, centimeters per minute, right?
What did you say the cross-sectional area was?
So this is the cross-sectional area is the diameter of the tube right there, the radius of the tube right there. So you have a lot of blood moving through here. If it's going at the same rate over here, right, it's gotta be going at a faster speed over there. And that's basically the big picture there. All right, so basically table 15.1, that gives the whole kind of big pictures of the what's going on in this whole, when we talk about blood flow moving through the body right there, right? And then we're gonna talk about more specifically the actual structures involved as it moves, as it leaves the left ventricle, right? So this, again, table 15.1 will give most of the information, right? So, when we look, we're looking at the heart as a pump, we want to look at it intact, one piece, your atriums, your ventricles intact. Like when we're talking about this discussion, we can kind of separate these two to give this more functional picture, kind of something like this, right? Pump over here, you're gonna leave the artery, it's gonna be under a lot of pressure, it's gonna move through, and the arteries are, we'll see, are gonna store a little bit of pressure because of the elasticity of the artery, right? That's gonna be the driving pressure into the arterioles. Over here, the final kind of pathway that are gonna lead into the capillary beds, right? We're gonna see that this is where we're really gonna control the flow into these capillaries. And this is what's basically gonna be the driving force for all our changes in blood pressure around here, right? Into here, and we're gonna leave the veins. Go back here, your veins are also gonna be distendable, they're gonna be expandable, they're gonna be a sort of a pressure, volume reserve over here, as we'll see, but we're gonna walk through this whole key right here, this whole chart right here, and by the end of this, you'll understand everything that's on the chart. Well, that's the goal anyway, right? So, leaving the heart, we're not gonna really talk about any of the tissue stuff, right? Again, I'm sick of it at me, but basically you have, the layers of the tube, you have a nice, smooth endothelium, simple squamous cells lining, or for laminar flow, moving through. On the inside, you've got some muscular layers, right, which will allow us to vasoconstrict and vasodilate, that is, change the diameter, that's important, right? Capillary beds are gonna be our exchange surface over here, where they're going to be leaky. There's gonna be no basically other layers right here, and this is gonna allow the actual perfusion, right, of fluid out here to feed the oxygen-starved tissue, right? And then the veins, again, is gonna be for return, but they're also very distendable. There'll be a so-called venous reserve here that's gonna hold blood that we can actually put back in the system later. These are the ones you can see a little bit about the layers right here, but this is the vessels we'll be talking about as we move through here. Right? And the arterioles, again, that final blood arteries going into the capillary bed, right? This is where we're going to talk about that resistance, right? We talk about peripheral resistance, it's going to be at the arterioles. Okay? So why are we talking about any of this stuff about pressure, right? This is the most really, I'll talk more about like a little bit more of the medical stuff, but next time, but this cardiovascular diseases are basically the biggest, health problem in America, so like, you need the right pressure. In the beginning, we talked about all those variables, right, about what you need to, what are the homeostatic regulation, right? Blood pressure, one is the main one. You need the proper amount of pressure, right, for perfusion of the oxygen and nutrient-starved tissue, right? If it's too much, right, or it's too low here, right, the pressure, the driving pressure into this capillary bed is too weak, right, and it doesn't perfuse correctly, right, and you don't get the oxygen tissue, the oxygen-starved tissue will not function right or die off, right, if the blood pressure going into these capillary beds are too low. That'll be called hypotension, right? The other thing about hypotension, if the blood pressure isn't strong enough to get up to your head, right, this is when you start passing out and stuff, right? The other bigger one in America is hypertension, right? Hypertension, that is, the pressure is too much for the vessel wall. Who had anatomy here in City College besides my student? Everybody in class 409, remember Al, the cadaver? Anybody have him? Remember Al? What do you have on his abdominal line? Anybody remember his aorta, abdominal aorta?
He had the little, like,
He had that big bulge in there,
Aneurysm.
right? That was an abdominal aneurysm. That was an aneurysm right there. And that was due to, at some point, the pressure on the vessel wall made it bulge out right there. Right? And it could also burst. You can get burst blood vessels over there spilling out into areas. Right? The other thing is, you know, it's an indication that there's a lot of peripheral resistance, right? Which is not good. There's clogged vessels. Something's not going on right. Right? And so basically all the blood pressure, which was flowing toward those, right, is being backed up in some way. You're getting higher blood pressure, right? Main things for, you know, in our modern society would be like too much salt, right? There would just be too much. Why would too much salt cause hypertension?
Fluid retention.
What's it?
I said fluid retention.
Fluid retention, right? Remember, salt follows water. If you have salt in your blood, right, you need more water, right, to kind of match that salt. So basically, it's keeping the water inside your blood, and that's going to cause high blood pressure, right? That's why if you have a high blood pressure, like 138 or something like that, no names, that's why, you know, they'll say, take a low salt, try out a low salt diet or something. It's just an indication of a lot of peripheral resistance typically. Right? And, all right, so that's why this is important, right? Talking about the right amount of perfusion into tissues. That's the blood pressure moving in, right? The arterial pressure moving in. All right, so when the blood leaves the ventricle, right, you get that contraction, right? That decrease of space, creating that driving force into the aorta, right? And let's say here the arteries are pressure reserve. The reason for that is when you squeeze this right here, all the pressure against the wall, the elastic arteries, especially the aorta right here, is going to expand. When it expands, it's not just going to keep expanding, right? There's elastic, everybody knows, like you pull out a rubber boom or something, rubber band or something like that, and you let it go, that elastic recoil, right, has energy. In other words, the elasticity has energy in it when it's blown up like this. And when you relax that, like when the ventricles relax a little bit, that recoil is going to push the blood forward right here, right? So that's going to maintain the pressure so that every time your heart beats, right, remember your ventricles go down to about, you know, very low pressure right here. But your arterial pressure is going to stay pretty high, right? It's not going to go down to zero. So your blood flow through your body isn't like stop, go, right? There's a pretty much continuous flow, right? Because this pressure reservoir of the elastic arteries moving through there. All right, does that make sense a little bit? I'll have to get that green balloon video. In any case, so yeah, so here's the ventricle, right? Very huge fluctuations, very high pressure, very low pressure at this point, right? You're going on down to almost low. But when you get to the arteries right here, that doesn't go down to zero because of that pressure reservoir, right? You do get a fluctuation in between the contractile force, the systolic pressure, and the relaxation, but it doesn't go down over here, right? That's pressure reservoir right here. You're maintaining that pressure because the arteries are acting as a pressure reservoir, right? And they're going to force that pressure is going to be transferred all the way through here, but of course it's going to decrease as we go along. Right? So there's fluctuations, systole, diastole, and then there's what's called the mean arterial pressure. That's something in between, not exactly half right there, but the mean arterial pressure, which we'll calculate in lab, or you already have right there, right? So the blood pressure is going to diminish as we go here, right, from the aorta, and basically by the time it gets to the capillaries right here, the blood pressure's got to be going into it, but it's going to basically decrease and decrease and decrease. Lowest pressure being the right atrium. Okay. So that mean arterial pressure, again, why this is important, this is the main measure, the main indicator of how much your general vessels are getting the right amount of blood, right? The degree of perfusion from the arteries into the tissues, right? This is why this is kind of an important value, right? Basically the blood pressure, right? The arterial pressure moving into the blood, right? This is why this is important. That mean arterial pressure, what that is a function of is how much blood is being forced out. Right? The heart, in terms of the stroke volume, in terms of the heart rate, because we know that's what cardiac output means. And then, because the flow is inversely proportional to the peripheral resistance, right? The peripheral resistance is going to play a role in this, right? how much resistance it's facing by the arterioles, basically. Right, so the volume of blood in the arteries, right, is gonna be determined by the input. This will be considered the input. The cardiac output is the input into the vessels over here, and then the flow out. Right, when we say out, flow out of the arteries, we're talking about the flow out of the arterioles into a capillary bed. They've left the arterial system into a capillary bed. So the volume of blood in the arteries is determined by how much is being pumped in and how much can get into the capillary beds. Right, does that make sense? How are we gonna phrase that for blood out? Blood in is from the heart, blood out is into the arteries, or into the capillaries. Right? So, bottom line, right, the cardiac output, peripheral resistance is gonna determine that mean arterial pressure, how much every stroke volume and your heart rate going into the whole arterial system, and then the arterial system kind of ends, right, into the capillary beds, right? So the rules here, right, we say the flow into arteries needs to be balanced with the flow out, basically, right? Basically, you don't want, if the arterioles are starting, if there's too much resistance out here, and if the flow into the arteries exceeding the flow out, that is, the arterioles are, let's all say, all constricted in area, and the volume in the artery, part of the blood system is gonna increase. That's gonna increase the pressure, which is gonna increase basically your mean arterial pressure, right? And the opposite is true. If your cardiac output is low for whatever reason, and your diffusion is very high, that is, it's very relaxed and dilated right there, the pressure overall in your body is gonna decrease. So you can change either one of those. You can change the cardiac output, or you can change the resistance, right? And your mean arterial pressure is gonna change. Right? Right? Then the other thing, that's about blood volume, right? In the arterial pressure, right? But the other thing is the blood volume in your whole entire body, unless you like drink a whole bunch of liquid and stuff, right? Mostly there's a little gain and loss, but it's relatively constant, right? But if your blood volume does increase for whatever reason, then your pressure is gonna increase. If your blood volume does decrease, then the pressure decreases. And one way you can actually increase the amount of blood in your arterial system is to kind of call up the troops from the veins, right? Your veins act as a pressure reservoir when your blood is moving from your, right? Moving from your legs or up through your abdominal area, through your liver right there, your vessels, the pressure on the vein walls will expand. They don't have that elastic recoil thing, they just kind of expand and sit there. And so you get this big so-called venous reserve inside your vessels that can be called upon if you have a sudden pressure drop in your arterial system. Right? If your MAP decreases to a certain point, we can call upon a little bit of blood in your veins right there. That is, your sympathetic nervous system is going to cause a little bit of constriction to force that blood back into the system. Because most of your actual blood is actually held in the veins right there. That's what venous reserve means. All right? So, let's take a look at this chart. Mean arterial blood pressure, right? That again, why it's important. This is the degree of the perfusion into the tissues, right? If you don't get that, you die basically if it's in the wrong place, right? And then mean arterial blood pressure, we talked about the cardiac output, that is the heart rate, the stroke volume, right? That's the blood into this arterial system right here, and then the blood out of the system, basically. Is going to be talking about that flow into capillary beds, right? The control at the arterioles, right? That how much blood is leaving those arterial system, right? So basically, in between here and here, right here, right? This is into the system, out of the heart, but into the arterial system. And this will be leaving the arterial system. Let's draw that red if we want here. And for this to be constant, we have to keep this balance, right? If we increase this right here, while keeping this, right, the blood pressure is going to increase, right? You're not changing anything, right? The blood pressure has just increased. Or you can do the opposite, right? If the blood pressure is the same over here, but all of a sudden you're increasing the resistance here, that's also gonna back up the blood over here, right? The peripheral resistance. And that's what basically what we talk about next time, related to a lot of, stuff, you know, diseases and stuff and clinical relevance to that, you know, peripheral resistance, right? So, any questions on that? Anybody need, that makes sense, sort of, in some sense, right? That's just a big, really basic overview, since I could, you know, have a little more time. But, so, it's Thursday. Yeah, so, if you have stuff you wanna ask about, then stick around, otherwise, I will see you in